The last topic of chapter 5, and that is the notion of conditional expectation in section 5.11. So once again, conditional expectation is something that is very easy to be confused about. But for the most part, once we have mastered it, it turns out to be one of the most beautiful and useful technique available to us. So let us define the notion of conditional expectation first for discrete bivariate random variable. So let x be x1, x2. We assume that they are discrete, jointly discrete. Then for any function g, we can define the conditional expectation of g of x1, given that x2 takes on the value little x2 to be nothing more than the summation over x1 of g of the value x1 times the conditional PMF is the conditional PMF of x1 given x2. And here we give it the value of little x2. So that's nothing more than, as we remember, for a discrete bivariate random variable, we have the conditional PMF. So the conditional expectation is nothing more than the expectation taken with respect to the conditional PMF. And the key point is the conditional PMF is a proper distribution. The conditional PMF defines a proper distribution or proper PMF. So this is well defined. And so the summation is once again over all x1 for which the joint PMF is bigger than 0, just to avoid summing over uncountable number of things. So we have implicitly assumed that the probability that x2 equal to little x2 is at least positive, because otherwise the conditional PMF is not well defined. So the main thing, and one thing that's very important to note, is that the conditional expectation of x1 given x2 is equal to some value x, little x2, is a function of x2, the value itself. So the conditional expectation is a function of the value random variable x2. And so like we said earlier, since the conditional PMF is a valid probability mass function, we can think of the expected value of g x1. So this has to say expected value of g x1 given x2 equal to little x2 is the expected value of that random variable under this new PMF or this conditional PMF. So if we no longer condition on the value of x2, then we can define similar quantity. So expected value of g of x1 given now the random variable x2. So this is now random variable. And so we have this sum. But here we have this x2 here is a random variable. So it's unspecified. And now this quantity here is now a random variable. So it is not a scalar. It is not a constant. This quantity here, let's try to clear out this page. Okay, so let me try to clear out this page here. This quantity here is a constant. It is a constant because it's a function of the value little x2, where x2 here is fixed. It's a constant. So in this case, this here is a constant. But in this case, if we do not tell you the value of little x2, or we do not tell you the value of the random variable capital X2, then this quantity here is now a random variable. In fact, it is a function, hx2 is a function of the random variable. Function of x2, the random variable. So it's another new random variable. So in the special case, when x2 is independent of x1, then in that case, this part here, in that case, then p of x1 given x2 is always equal to p of x1. In which case, then by that definition, we would then have expected value of g of x1 given x2 is the summation of g x1 p x1, in this case p1 x1, and so that's the same as expected value of g of x1. So in the case when they're independent, if x2 is independent of x1, then this reduces down to a constant. So let's try to reiterate that. If you condition on the value of x2, say x2 equal to little x2, then you have a constant. If you do not condition on the value of little x2, then you have a random variable. But if the random variable is independent of x1, then that random variable, hx2, reduces down to a constant. So a constant is a random variable, just as a very special random variable. So the key point here, and this important observation, which is not really that important for the level of our class, which is 421, but maybe much more important if you want to understand conditional expectation at a higher level. Say when you go to, say, like, take graduate level class, is that for any set A, the expected value, so this is now a constant, because the expected value, there's no conditional. The expected value of gx1 times the indicator, this is the indicator that capital X2 belongs to the set A. So we can write this as basically this combination where we sum over x1, and because x2 has to belong to the set A, so you sum over x2 belong to A. So now you have the function g of x1 and the joint PMF, and due to the fact that the joint PMF can be factored into the marginal PMF for x2 multiplied by the conditional PMF, so conditional PMF and the marginal PMF for x2. And so now if you change the order of summation, this inner sum here, we see earlier, is nothing more than expected value of g of x1 conditioned on the random variable x2. And now if you multiply by the indicator that x2 belongs to A, so you're going to sum over p2 of x2, then this is now a double expectation. So this result here is a little bit confusing at first glance. So let's try to unpack it. So the way to unpack this is that this is an unconditional expectation. So this is a constant. This constant can be written as the expectation of some conditional expectation. So the expectation of g of x1 given x2 is, as we said earlier, it is a function of x2. So now we can think of the inner sum here. So we can therefore think of the expectation of g of x1 given x2 times indicator of x2 belong to A as basically h of x2 times indicator of x2 belong to A, which is another function of x2. So let's say h tilde of x2. So then the inner expectation here is nothing more than the expectation of h tilde of x2, and so it is done with respect to x2. So that is a bit of a mouthful, but try to go back and think a little bit more about this. All we're saying is that the expectation of both x1 and x2 together can be thought of as being two parts. The first part is take the expectation of x1 conditioned on x2. That gives you a function of x2. Then now take the expected value of that function with respect to x2 to give you everything. So for example, if you take a belong to the real line, in which case the indicator x2 belong to a is always going to be true, because x2 always belong to the real line, because it's a random variable. So therefore, expected value of g of x1 is nothing more than expected value of g of x1 is going to be expected value of g of x1, indicator x2 belong to the real line. So that's what we have here. And so we have, by the previous result, we can think of the conditional expectation with respect to x2 and take the unconditional expectation with respect to x2 outside. And because this is always equal to 1, we have this is known as Tower property. So in summary, you can take the expected value of x1 by first taking the expected value of x1 conditioned on the random variable x2. That gives you a function of x2, and then take another expectation with respect to x2 of that function. So the Tower property turns out to be very, very, very powerful. I cannot underemphasize that. In fact, most of probabilities in the, say, more advanced level are based on, can I somehow be smart about conditioning? Okay, so we see a few examples of these kind of techniques in a few lecture slides. But for now, let us define the notion of conditional expectation, but this time for bivariate continuous random variable. So with x be to x1, x2, then for any function g, we can now define the conditional expectation of g of x1 given x2 equal to little x2 as the integration of gx1 with respect to now the conditional PDF of x1 given x2. Another integration is with respect to x1 itself. So once again, I just want to emphasize is that this given x2 equal to little x2 is potentially ill-defined because once again, the probability that x2 equal to little x2 is always equal to 0. This is the problem that has annoyed us when we talk about, say, conditional PDF or, say, marginal PDF or so on and so forth for continuous random variables. Here, once again, we have the same kind of like issue, but as we see that we can ignore it for the most part, we will try to ignore it here as well. So this we can take this as the definition. We can take this as the definition and don't have to worry too much about whether this is well defined or not. In any case, once again, just to continue the previous point, this here is not a valid expectation because this probability is always going to 0. Nevertheless, as we see earlier, this conditional expectation is a function of the value little x2, such that for any set A, we can still write this the expected value of gx1 indicator x2 belong to A as this double integration. So first we want x2 to belong to A, so we only integrate x2 with respect to the set A, and then we define by definition gx1, the conditional expectation, to be this term. And so once again we still have that we can define expected value of gx1 indicator x2 belong to A to be nothing more than the expected value of gx1 given x2, and the indicator x2 belong to A, just like in the discrete case. So in summary, if we take this as a definition of conditional expectation, then the discrete case and the continuous case have the same definition, and furthermore we don't have to worry about the fact that the probability that x2 equal to x2 is equal to 0. So once again, this is mostly as a technical aside that would turn out to be quite useful or important if you want to take more advanced class in probability. But at the level of our current class, this is, like I said, just a technical aside, so we don't have to worry about that. Okay, in any case, continuous or not, once again, we still have this relationship. We still have this tower property, that the expected value of g of x1 is obtained by first conditional x2, which gives you a function of x2, and then taking the conditional expectation with respect to x2 of that function. And finally, if I let the set A be some small interval around little x2, then I can define that the interpretation, I can interpret that conditional expectation as roughly this conditional expectation, which is well defined. So that is how I could try to give meaning to this possibly ill-defined quantity here. Okay, so let us see a quick example. So suppose I have y, which is y1, y2, which is jointly continuous with the PDF of this form. So this PDF is, once again, will look like 0 and then 2, the 0 and 2 square. And then this is the line y1 equal to y2. And so it will look like this is the area which is defined. So in order to find the expected value of y1, condition on y2 equal to y2, assuming the interpretation as we saw before, then what we need is we need to find the conditional PDF. And the conditional PDF is obtained by looking at the joint PDF divided by the marginal. So joint divided by the marginal gives you conditional. Since we already have the joint, we don't need to determine the marginal. And the marginal for y2 is, just have to be careful, is integrated with respect to y1, but due to the constraint y1 less than equal to y2, therefore y1 can only go from 0 to at most y2. And this is simply y2 over 2. And so the conditional of y1, conditional on y2, the conditional PDF is 1 over y2. So this is y1 conditional on y2 equal to little y2 is uniform on 0 and y2. So that's a conditional PDF of y1 conditional on y2. And so to get a conditional expectation, we just have to integrate the conditional PDF and then this random variable y1. And so this is a simple exercise. And so we have y2 divided by 2. And this emphasizes the point is that this is a function of y2. So the conditional expectation is a function of y2. Just what we said earlier. So now let us do another interesting example. And this illustrates the tower property. So suppose I have x and y are uniform. X and y independent. And I want to find the distribution of the product x times y. So we see this again in chapter 6. But let's try to show it via the tower property. So the probability that z less than or equal to z is the same as the expected value of the indicator that z is less than or equal to z. That's what we saw earlier in, say, like way before in chapter 3. So the probability of an event is the expected value of the indicator of that event. So that's the expected value indicator that x, y is less than or equal to z. Now we could apply the tower property. So we first conditioned on y and take the conditional expectation. And then we unconditioned on y on the outside. So if I conditioned on y, then that expected value, the outside expected value, conditioned on y, is simply this term, because this is a function, because expected value of indicator x, y less than or equal to z, condition on y is a random variable, hy. So that is this quantity here. And because y is uniform, so the PDF is dy. So now because you're already conditioning on the value of capital Y equal to little y, so that's the same as saying that expected value of the indicator that x, the random variable capital X, times the value little y is at most z. Okay? And these are conditioned, and so that's the same as by, once again, by the fact that the probability of the event is the expected value of the indicator of the event. So this indicator that x, y less than or equal to z is an indicator that x less than or equal to z equal to y. So that's the same as probability that x less than or equal to z over y. And because of uniform, that is equal to z over y. Okay? Oh, oops. But now we have to be a little bit careful. So we come to this point. But now we have to be a little bit careful. We have to be careful about the value of y. So if y is less than z, then z divided by y is going to be equal to 1, in which case the probability that x less than or equal to 1, z divided by y is less than or equal to 1, or bigger than or equal to 1, z divided by y is bigger than or equal to 1. If y is less than z, then z divided by y is bigger than or equal to 1, in which case the probability that x is less than or equal to 1 is always equal to 1. So that's why if y goes from 0 to z, the probability is 1. Meanwhile, if y is bigger than z, then the probability that x less than or equal to z divided by y is equal to z divided by y itself. So here we have to split to two parts. One part goes from 0 to z, the other part goes from z to 1. But this is once again a simple exercise in integration, and so you get z minus z logarithm z. So this here is the distribution of z equal to x times y. And by taking the derivative of this one, we can easily see that the PDF of z is going to be equal to 1 minus ln z, and then minus 1. So that's minus ln z for the PDF. So as another example of the power of the tower property, suppose I have y1 and y2 be independent standard number, and I consider the product y1 times y2. Then what is the marginal, then what is the moment generating function of u? Well, using the tower property, we have expected value, the moment generating function, which is expected value t times 2 power of u. That says t y1, y2. And so now we can first condition on y2. So that's the expected value condition on y2. And then unconditioned with respect to outside. So we know that if I conditioned on y2, then expected value of exp of ty1 is by definition, because y1 is standard normal, that's just going to be the moment generating function for standard normal is nothing more than exp to t mu, mu is 0, plus t squared sigma squared is 1, divided by 2. So that is exponential of t squared divided by 2. So now if I conditioned on y2, then I could let t y2 to be a new t star. So therefore I have t star divided by 2. So this is t star divided by 2. So I will have that is a moment here. I think I may have messed up something. Okay, so this should be expected value of exp. This is a typo. Expected value of exp. So this is not true. Actually, this is supposed to be. Let me fix that. This is supposed to be expected value of exp of t squared y2 squared divided by 2. But by the default definition, I know that y2 squared is chi-squared with 1 degree of freedom. So the square of a normal is chi-squared with 1 degree of freedom. So in this case, I could now let t squared divided by 2 be another new t, that's called a t tilde. So this is nothing more than expected value of exp of t tilde times a chi-squared with 1 degree of freedom. And I know the moment generating function for that one is nothing more than 1 minus t tilde to minus 1/2 with, say, 1 minus 2 t tilde minus 1/2. And now I replace t tilde to be t squared divided by 2. So I will have this as the correct answer. So the answer is still correct, but this part here is wrong. So in any case, once again, by using the moment generating function of the chi-squared, which is moment generating function of chi-squared, just to repeat, t squared divided by 2 y2 squared is going to be equal to 1 minus 2 t squared divided by 2 to minus 1/2, which is 1 minus t squared divided by minus 1/2. Because as we see earlier, expected value of exp of t of y squared is 1 minus 2t to minus 1/2. In the case of, this is the MGF of chi-squared. So that is how we get this moment generating function here. Okay. As another example. So this is example 5.32 in your textbook. That says that a quality control plant for an assembly line involves sampling 10 finished items per day and counting y, the number of defectives. So P denotes the property of defective, so then y is binomial NP, but P is now uniform from 0, 1/4. So we want to find the expected value of y. And this problem, we note, doesn't fit exactly into the two definitions above, because the pair yp is neither bivariate continuous, because y is discrete, nor bivariate discrete, because p is continuous, but rather it's a mix of discrete and continuous random variable. So there is neither a conditional PDF nor a conditional PMF for y given p. So your textbook just sidestep this issue by using the Tower property. So nevertheless, we can do the same thing by just using the tower property, but maybe let's try to be a little bit more, say, careful to see what exactly are we trying to say. So we can interpret the problem as saying that the marginal PMF for y can now be written as this form. So this is the binomial NP, and then this part is the P is uniform from 0 to 1/4. So we can take this as a definition of the marginal PMF for y. And so you can evaluate expected value of y to be just the expected value with respect to this marginal PMF. And now you could interchange the order of integration and summation. So this is what we meant by saying that this will look like the expected value of y given p. That's the tower property here. And the tower property here is nothing more than interchange. It's nothing more than interchange of expected value of integration and summation. So expected value y given p is still np, and then now expected value with respect to p is n over 8. So like what I said here, this behaves exactly like the tower property there. So what your textbook did is perfectly correct, but it doesn't follow directly from the definition of the conditional expectation. And that's just because we have not really defined the conditional expectation in the case when one random variable is continuous and another is discrete. To define that properly will require much more complicated machinery that's outside the scope of our current class. But the main thing is that the tower property is still correct, and you can always use it without caring too much about what exactly is going on in the background. So we will soon end our discussion of chapter 5 with another very important result, which is the law of total variation. So you may want to take a look at this result and compare it again against chapter 4, section 11, in the case of mixture. So this was optional, so we will not include it in our class here. But we will include this, we will use this in maybe later on in 422. But in any case, let x1 and x2 be two random variables. They don't have to be discrete or continuous. They could be one discrete, other continuous. They don't have to be both discrete or both continuous. Okay? In any case, we can define the conditional variance of x1 given x2. So the variance of x1 given x2, we can define exactly like what before. So that's expected value of x1 squared given x2 minus the expected value of x1 given x2 itself, everything squared. So once again, this is a function of x2. We always want to emphasize that. So the conditional variance is a function of the random variable x2. It is a random variable. And the main result that is quite useful is that the variance of x1 can be split into two parts. The first part is the expected value of the conditional variance, expected value of conditional variance, plus the variance of the conditional expectation. So that's the easiest way to remember it. The variance of a random variable is the expected value of the conditional variance plus the variance of the conditional expectation. Well, now you can condition on some other random variable. And so the proof is quite straightforward. There is really no point to elaborate. All we have to do is set the expected value of the conditional variance. Remember to use the property, the tower property, to get this term. And this is just keep it as is. And for the variance of the expected value, the first term is just what it is, which is this term. And the second term is once again the tower property. So we just have to apply two tower property. And adding them together, use the claim. So let us see the power of the conditional variance or the law of total variance. In many problems, we can think of it as being multi-layered. You have a random variable that depends on another random variable. So a simple example is as follows. A hand lay x, capital X, where the number of x is Poisson with rate parameter lambda. Now each of the x hatches with property P, and these x are independent of one another. You have in total capital Y chicken chicks. So a hen lay capital X, number of x, each of these x hatch with property P. So we want to find the number of chicks at the end of this process. I want to find the variance. So the expected value of y is easy, tower property. So if I know that I can first condition on the number of x, because y given x is binomial with x p, so that's just x times p. And now I can take the condition, I can take the expectation with respect to x, because x is Poisson, expected value of x is just lambda. And p is a constant, so don't have to worry about that. It becomes lambda p. Using the law of total variance, the variance of y is the expected value of the conditional variance plus the variance of the conditional expectation. So the expected value of y given x, we already know, is xp. So we just need to evaluate variance of xp. That's what we have here. And then the variance of y given x, because we know that y given x is binomial xp, so therefore the variance of y given x is nothing but an xp 1 minus p. So we have the other part here, as well as xp 1 minus p. And using the fact that x is Poisson, you can easily show that's going to be equal to lambda p. So the mean and the variance is equal to lambda p, which will suggest right away that y is Poisson with rate parameter lambda p. And we showed this earlier in, say, like chapter 3, that indeed y is Poisson. But as you can see here, this is a very useful thing to know. We can just compute the expected value, and we can just compute the variance, and we can form a hypothesis. The hypothesis here is that y is Poisson. With that hypothesis in mind, you can go back and check whether it really is Poisson. And so this allows you to avoid the discovered new result that you can then go back and show, of course, it has to be that. So the law of total variance is very, very powerful. As another example, suppose I have a random variable n that is taking positive integer. And then now I let the random variable s be the sum of n copies of the xi. Each of the xi have the same distribution. So now n is independent of the xi, and I want to find the expected value of the sum and the variance of the sum. So you can think of this as follows. Suppose I generate n via a Poisson process. So I was able to get, I want to go and look at a random number of say boxes. So I first sample how many boxes I will check. That's my capital N. And for each of the box, I will go in and say maybe like pull out a few balls. And if the ball is red, then I will keep track of the number of red balls. So at the end of the day, I say how many red balls do I have. The number of red balls is determined by the number of boxes I chosen, which is random, and then determined by the number of the sampling scheme for each box, which is also random. So that is the x1 to xn. So what I want to do is find the number of balls I get and the variance. And once again, by the Taylor property, this is as easy as you want. So expected value of S is expected value of S conditional on N and unconditional with the Taylor property. So because N, you already know what N is, and you can think of this as a constant, so you can think of this as expected value of S conditional on N to be the same as expected value of x1 plus expected value of x2 plus dot 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 plus expected value of xn, because n is supposed to be fixed. So you have n times x1. So you could just get, now this is a constant, you can move it outside. So just have expected value of n times expected value of x1. Just like what you would expect. The number of balls in each box times the number of boxes you are expected to see. In contrast, the law of total variance turns out to be quite elegant. The variance of the conditional expectation plus the conditional expectation of the variance. The conditional expectation we already know is n times expected value of x1. So therefore, you will multiply out to have expected value of x1 squared times variance of n. And then expected value of n times variance of x1. That's once again easy because x1 up to xn are independent. So the expected value of the variance of the sum is the sum of the variance, so it's just n times variance x1. And you have a simple formula here, which work for any choice of distribution x and for any choice of random variable capital N. So the mean and the variance turns out to be quite clean and really does not depend as much on the specific distribution. So as we can see, this result is very powerful because I don't care what is the distribution of n, I don't care what's the distribution of x. If I want the mean and the variance, I just need to know the mean and the variance of n and of x. So finally, we come to the topic of the best predictor. This topic will not be covered in this class, so I will skip it, but I just want you to take a look at the lecture slide. But the main thing is that this question here, and I think it's a very important question. So you have the two random variables x and y. Suppose I know the information about y, then what is the best predictor for the random variable x? We know that because x and y are random. If I told you the value of the random variable y, what then is the best prediction for my random variable x? And it turns out the answer is nothing more than the conditional expectation of x given y. And the product and the proof is very simple. So we shall not discuss it anymore. But in summary, that in the case when y are independent, then x and y are independent, then the conditional expectation is the same as the mean. So therefore, if there is no useful information about x given y, then the best predictor is always the population mean. And we see that in the exercise in chapter 4. But in summary, this is a very important property of conditional expectation. That is, the conditional expectation of x given y is the best prediction of x, given that the only thing you know about it is the random variable y. So with that, we will end here for today. Good luck on your second midterm. And from next week, we will start to upload some materials on chapter 6, which will hopefully end this semester. So take care, and if you have any questions, please send me an email. Have a nice day. Bye.